Okay, so let's start. Okay, so let's start with the first problem. So, by the way, you can pop up anytime, or you can raise your hand and you can ask the question, or if you want to clarify anything, you can ask to clarify. Okay, so let's start. So this is the problem where we are testing the students' understanding of the Faraday's law. So it says that, the diagram below shows a rectangular circuit. So this is a rectangular circuit of dimensions A cross B. So A cross B, and it is consisting of n turns. So it's an n turn. So it's a rectangular circuit, or a rectangular coil, you can say, which is of n turns. And now what I'm doing is I'm placing this circuit in a magnetic field. So I'm placing it in an external magnetic field, and this is the external magnetic field. If you see here, it is AY B0 cosine gamma Z cos of omega t plus beta y Weber per meter square. So it's in the y direction. That means it is coming out of our screen, because this is my y axis. This is my z axis. Sorry, it is AX, not AY. So it is coming out of the screen. And we are told that B0, B0, this gamma, and this omega, and this beta, they are all some constants. Now we need to derive the expression for the EMF, which is developed in the circuit due to the Faraday's law, because our coil is placed in the time varying magnetic field. See here, if you look at this expression, this is telling that my magnetic field is time varying. So in this case, as we have already taken in the lecture, the easiest way to address these kind of problems is to use the Faraday's law, which says that EMF is equal to minus N d psi over dt, or it is minus d uppercase lambda over dt, where my uppercase lambda is nothing but n, my uppercase lambda is nothing but n times psi. Okay, so this is the expression, at least in my lecture, I told that this is the expression which is the most easiest one to apply, because you have seen that this will take into consideration any type of EMF, whether it is motional EMF or transformer EMF. So we don't need to worry about which type of EMF is generated by this circuit. So if we use this expression, it will automatically take into consideration whatever EMF is generated by the circuit. So by the way, this kind of circuit, so what type of EMF this kind of circuit is generating? Because you have a time varying magnetic field and your coil is a stationary. Your coil is stationary and it is placed in a time varying magnetic field. So the type of EMF that you will get is a transformer EMF. Okay, so you know the big expression of the transformer EMF, which you have taken in the lecture. You can use that. I'm not saying that you cannot use it. You can use that, but that is a little bit time consuming, because you need to find out which would be the best approach. So therefore, always try to go and look for the best approach. We know that you can also use the transformer EMF, which is closed line integral E bar dot dl, or it is minus integral over the surface dou B bar over dou T dot ds. This is the expression for the transformer EMF, right? So you can use that. You can use and you can solve it. But here, the much easier way is this one. That means you need to first find psi. So how do you find psi? Psi is nothing but the flux, the magnetic flux, which is through this coil. So we need to find the flux which is through this coil, which is through this closed area, which is through this surface, which is enclosed by your closed line integral or your closed loop. So therefore, we know the formula that psi is integral b bar dot ds bar, right? So here integral, what is your b bar? B bar is known to us, which is ax b0 cosine gamma z cos of omega t plus beta y. Now ds. So now here the important part, whenever you are applying this expression, it is very crucial that you identify your ds properly. And to identify ds, you have to look for the EMF. This is what I always tell my students in the lecture. Look for your EMF polarities. And always you need to integrate from negative polarity to positive polarity. Okay, so here we are doing the surface integration. So therefore, in my surface integration, what I need to do, I need to use my right hand rule, and in the right hand rule, my curving of my 4 fingers, it should go from negative terminal to positive terminal. So it should go from negative terminal to positive terminal. So if you want, I can draw here. So this should be my fingers, my 4 fingers, right? And if I do like this, then my thumb will be going inside the screen. You can do it. So go from negative to positive. Okay, move your fingers. So your thumb will be in the direction inside the screen. It will be in the direction inside the screen. So that will give me the unit normal to my ds. So therefore, my ds is, I can see the ds. So it is dy and dz. Very simple. It is dy and dz. But what is my unit normal? So you will find it from the EMF. So move your fingers from here to here, which is what I'm doing, here to here. And this is my thumb, which is going inside the screen. So therefore, it is minus AX bar. And this is what I'm getting here. So this is the only crucial part whenever you apply this expression. So minus AX dy dz. Now problem becomes very straightforward. So your integration limits for your z is from 0 to b and y is from 0 to a. Then you have AX, it should be a dot here. So it is AX dot AX will be 1. So your minus goes outside and this is your expression. First, it is with respect to dy. So therefore cos of gamma z sine of gamma z over gamma, and the limits are from 0 to b. Then cos of omega t plus beta y, you have to integrate it with respect to y here. So it is sine of omega t plus beta y over beta, and the limits are from 0 to b. So when you do this, this is your flux. And once you have flux, then EMF is minus n d psi over dt, and then take the time derivative of this one, and this is your answer. Okay, so it is very straightforward, especially when you use this expression. It becomes very straightforward. Now the only key takeaway message is, how do you find your unit normal to your surface ds? Okay, which has to be the right hand rule, and your curving of your fingers should go from the negative terminal to the positive terminal. And the thumb will give me the unit normal direction. Okay, so this is the first question. Now let us go to the second problem. So second problem is again, yes.
Yes, please. Is there any case that we can't use the flux equation?
Flux equation, especially whenever you are using, from my experience, if you use your motional EMF, even with motional EMF, using flux and finding the expression using flux is okay. You would be able to do it. The other way around I can give you, but I do not see any examples where this expression is difficult to apply and the other expressions are easier to apply. I did not see this in any problems as far as I remember. But I cannot say it 100%.
Okay, thank you.
Okay, yeah, other way around, yes. So other way around, for example, for your motional EMF, which I told you that, sorry, for your transformer EMF, which I told you, minus integral over surface dou B bar over dou T dot ds, or for your motional EMF, which is equal to closed line integral E bar dot dl, or it is closed line integral U cross B, U bar cross B bar dot dl. Yes, in some cases, applying this becomes very difficult and this becomes very easy. Especially, there is an example in your textbook where your loop is rotating. So when your loop is rotating, I think it's example 9.2. So when the loop is rotating, you will see, the way that your book has derived, your example has derived is your example, the example has used this expression to derive it. And you will see that it's quite complicated. But I would suggest you to go and try using this expression to derive that. Then in this case, it becomes much easier.
Okay, clear, thank you.
So let's go to the next question. So here is another question. So the question says that you have an infinitely long straight conductor as seen in the figure. So this is infinitely long and it is carrying a current of I naught cosine omega t. So this is the current which is carrying. And the figure also shows a coplanar n-turn rectangular loop. So that means both are in the same plane. That's why it is coplanar. And this is my rectangular loop, which is made up of any wire or anything else, and it has n turns. And they are situated in the YZ plane. So it is situated in the YZ plane. Both the straight line carrying conductor and the rectangular loop are situated in air. So that means our medium is air. Develop an expression for the EMF induced in the rectangular loop. So here we need to find the EMF induced and also see the terminals, the polarities are given to us. The width, the length is W and the height is H, and this is mu0 and epsilon 0 because it is an air. And this is the distance A. So how we are going to approach? So our objective is to find the EMF. So to find the EMF, first we need to know that where is our external magnetic field. Okay, we need to know where is our external magnetic field. So who is developing that external magnetic field? So in the previous example, the external magnetic field was already given to you. But in this example, the external magnetic field is not given to you. See, it's not given to you. So first, our objective is to find what is the external magnetic field here, who is influencing my rectangular loop to generate this EMF. And this external magnetic field is coming from this. So this is becoming the source for that external magnetic field. So this is my infinite long conductor, straight filamentary conductor carrying current, which is a time varying current. So we know that this time varying current will introduce the magnetic field in the phi direction. So phi direction will be going into the screen. So it will generate the magnetic field in this direction. Although it is time varying, so it will change the direction, but I'm just showing it to you. So it will be moving in this direction like this. And then after half the cycle, then it will be moving in this direction. But this will be the external magnetic field, or which under the influence of which your rectangular loop will generate the EMF. So first, we need to find that external magnetic field. So how do we find? We know it very well that H bar is I over 2 pi rho A phi, right? So this is our magnetic field, which is generated by this infinite long filamentary conductor. So now what I can do is, it is in air, so therefore I want B, I don't want H, because for here I want B. So B is mu H, and since this is air, so therefore B is mu naught times H, mu naught times H. Now I will substitute the current. So what is the current here? Is I naught cosine omega t. So therefore my B bar is mu naught I naught cosine omega t over 2 pi rho A phi. So this will be the magnetic field here, everywhere. And this magnetic field will change its value, yes, because it depends on rho, so how far you are. But this is our magnetic field, although it is being generated by this infinitely long straight line conductor, but this magnetic field is external to this loop. So therefore, now what I will do, as we did it in the last example, we have to do the same. So first, let's find the flux. That is flux through this surface, which is enclosed by my rectangular loop, psi, which is B bar dot ds bar. And now B bar is my this one, because this is my external magnetic flux density. Flux density to this loop, to the rectangular loop. So therefore, you have B bar, so substitute it here, see, mu naught I naught cosine omega t over 2 pi rho. Now ds. So again, as I told you in the last class, in the previous example, finding ds is very important here. So ds bar. So what will be ds bar here? So my ds bar will be, again, put your fingers and then try to move from minus to plus. So if I try to move from minus to plus, here my thumb is coming out of the screen. See, go from minus to plus, the thumb is out of the screen.
Minus A rho.
So minus A phi, yes. So it will be d rho dz minus A phi. And this is mu naught I naught cosine omega t over 2 pi rho times A phi. Dot product with this one. So dot product with this one. So therefore, you will get minus this one d rho dz. Okay, so this is my B bar. Dot product with ds. Now, your integrals. So if you see, I need to integrate over d rho and dz. So it's in the cylindrical coordinates, guys, please, because we know that our external magnetic field is in the cylindrical coordinates. So therefore, the integrations that we need to do here is in the cylindrical coordinates. So for your dz, so your dz, my height is, this is my height. So therefore, for dz, it is very straightforward. I can assume this to be z0, something constant like z0. Then this will be z0 plus h. See, so z0 plus h. And then my rho. So my rho, I have to integrate from here to here. So here is my rho is equal to a. See, because this direction is my rho direction. It's clear? So this is my rho direction. Then what will be this one? This will be my, this is, this is W, then this will be rho is equal to A plus W. So therefore my rho is A to A plus W, and my Z is from Z0 to Z0 plus H, and this is my integration. So once you integrate, you will get this. And by the way, you will see that Z0 will, this Z0, which you put used as a constant, this will cancel out. So you will get this as an answer. And then your EMF is minus N d psi over dt. Take the time derivative of this and multiply it by N. So this is my EMF. Clear? So this is another example on the Faraday's law. So let's go to our problem 3. So in problem 3, we are testing the students' understanding of our phasors and our T wave. So what is the question? The question is saying that in free space, for a sinusoidal time field variation, which has an angle of omega, the phasor magnetic potential is given by this. So magnetic vector potential is given to you. So A bar, remember the magnetic vector potential is given to you. Now it is A naught e power minus j beta x A bar, because it is now time varying. Why? Because my magnetic field is time varying, therefore my magnetic vector potential is also time varying. This is given to us, where A0 and beta are some constants. Now, what is asked? We need to find the corresponding phasor electric field intensity vector. That means we need to find E bar. So how are we going to, what will be the approach? How are we going to proceed? Any tips? Because magnetic vector potential is given to us. So in this case, how we should think? So you should first think from the point of view of magnetic vector potential, and E is asked. So if electric field is asked, I know there is no relationship between E and magnetic vector potential. So I have to think in this way. Okay, I want E. Now, first, can I find H? Can I find H? Because from H, I can find E. We have seen this in TEM waves. The corresponding or the associated E I can find using Maxwell's equation. So therefore, let us find this H bar. And to find H bar, we have to find B bar. And do you have a relationship between B and A bar? B bar and A bar? Yes.
Yes.
Yes. Del cross A bar is B bar. So therefore, we will use this expression and first find B bar. From B bar, you can find H bar, and then use the Maxwell's equation. Then you can find the associated or the corresponding E bar. So this has to be the approach. So this is what it is. So in this problem, guys, the only thing is you need to just wait, give a pause for a minute, try to think how you should proceed. And once you are clear with your steps, straightforward, submitting and, substituting in the equations and finding nuls. See here. So first I'm finding the phasor of BS, which is del cross AS. So I'm putting my A here, and then I'm getting my BS. So this is my BS. J beta A0 e power minus J beta X A bar. Then HS. HS is what? BS over mu naught, because it is free space, air. This is given to us. So therefore, I got HS. This is my HS. Now, from HS, you can find your ES. You can find the corresponding ES using the Maxwell's equation. So this is the Maxwell's equation. Del cross HS is J omega epsilon ES. Remember, so del cross H is J omega epsilon ES. So this is our Maxwell's equation. So put it in the Maxwell's equation. So what I'm doing is I'm first putting the left-hand side. So this is my left-hand side. And this is equal to this one. And therefore my ES is this one. And if you put it, if you simplify it, you will see that my ES will be AC. Is it correct? You can check because we know that E cross H should be the direction of propagation, right? What is the direction of propagation? It is minus J beta X minus X. So it is in the positive X direction. This is the direction of propagation. So therefore, this is AX. Now my magnetic field is AY. So it is AY. So what should be E bar? E bar should be AZ, because AZ cross AY will be minus AX, but here it is plus AX. So it should be minus. So that's why you see okay. Got it?
Yes.
Another way, without even using this, how can I get it? We know. What do we know? We know that eta is equal to HY over EY over HZ. And what is your eta? Root of
Mu over epsilon.
Mu naught over epsilon naught. Just a second. Can we use this? Yeah, we can use this, but yeah, you can use this, but you need to, simplify. So you can still use this. So what you can do, so from here you can find your EY. So which is nothing but HZ times eta. So what is your HZ? Is this one. So J beta A naught over mu naught times eta, root of mu naught over epsilon naught. Correct? E power minus J beta X times AZ, because AZ and negative we already got here. And the direction of propagation for electric field, associated electric field, will be same as for the magnetic field with the same beta value. So this amplitude, you can get it with the. So I think if we simplify this, we should be able to get the same answer. Let me see, or maybe you guys can also help me. So it will be minus J beta A naught over mu naught root of mu naught over epsilon naught. So there is an omega also here. So
beta multiplied by the 1 over square root of mu multiply by the epsilon is equal to omega.
I think this is one. U is equal to omega over beta, which is 1
Yeah.
root of mu naught
Yes.
epsilon. Yeah.
Yes. Okay.
If you substitute this, I think you should get the answer. So root of mu naught epsilon. So this, I think you can substitute here. So this will be minus j beta a naught. So it is 1 over root of mu naught epsilon naught. Yes. So it is equal to omega over beta. So minus j beta square a naught over w. It is root. This root of mu naught epsilon naught. It is u is equal to omega over beta. I think you should get it, guys. I'm just leaving it here because of the time constraint, but you can substitute, and I'm sure you should get this one. Okay, so I will leave it to you. So you should get this one because they are the same. So whatever we have studied in TEM waves is actually coming from this Maxwell's equation. So we should get the same answer. So rather than applying this way, you can directly find the EY using this expression. Okay, so I will leave this to you, but you can do it at home. So let us move further. So okay, let me clear it. So next, let's go to the next problem. So this is the displacement current density. So we are assessing the displacement current density knowledge. So what it is saying, so here you have a coaxial capacitor. So you have a coaxial capacitor. Okay, so you have a coaxial capacitor of length 6 centimeters. So length is 6 centimeters. And it is filled with the dielectric material of epsilon r. So that means this dielectric material is of epsilon r as 9. The radii of the inner and the outer cylinder conductors are 0.5 and 1. So the inner, okay, so its radius, how can I show it? Okay, something like this. So its radius is 0.5 and the outer conductor radius, this one, is 1 centimeter. If an applied voltage across the capacitor, so it is connected to a voltage source and it is up, and that is generating an electric field of this. So this is an electric field which is being generated in the dielectric. See, it is being generated in the region between the two cylinders. That means in this dielectric region, this electric field is generated because of applying a voltage. Now you need to find the displacement current. So you need to find ID, displacement current, which is integral J bar dot ds bar, JD bar. So you need to find the displacement current density, because once you know the displacement current density, you just integrate it over this area. See, integrate it over the area of your dielectric. So if you integrate the area of the dielectric, then you will get the displacement current, because we know the displacement current exists in this dielectric region because of this electric field. Because of the time varying electric field, see, it's a time varying electric field, you will get a displacement current density which is existing in the dielectric region. So if you integrate the displacement current density over the region of dielectric, you will get the displacement. So our objective is to find J d bar. And how can I find J d bar? Yes, how can I find J d bar? We know the expression. Remember, what is J d bar? Is dou d bar over dou t. Remember? This is very important contribution of Maxwell. So J D bar is dou D bar over dou T. Or I would say epsilon dou E bar over dou T. Now, this is epsilon naught, epsilon R, dou E bar over dou T. And what is the epsilon R of our material? 9. So 9 epsilon naught, dou E bar over dou T. So 9 epsilon naught. Now take the time derivative of the electric field. This is the time derivative of the electric. Okay, and A rho. So once I get JD bar, then the current is what? J bar dot ds bar, material. So the length is 0 to L, which is the length of the capacitor, and the dielectric material, it is circular. So therefore, if you see here, you have phi and you have Z. So therefore, Z is nothing but the length of your capacitor. That's why it is 0 to L, and phi is the complete 360 degrees to cover the complete circular area or the circular part. That's why it is 0 to 2 pi. And when you solve it, this is the current. So this is the displacement current. Okay. So this is how you can find the displacement current or the displacement current density inside any capacitor. Now, so let's go to the next example. So this is again an example where they are testing the Faraday's law. And this example is very similar to what you guys do in the lab. Okay, remember in the lab, you have an experiment, and if I'm not mistaken, it is experiment number 7, where you will look at the EMF. So it's very similar to experiment number 7. So what it is saying, in free space, 100 turns square loop of side 0.5 meter is placed in the XY plane. And the loop is subjected to a magnetic field, which is a time varying magnetic field. See, cos of omega t is there. Then what is the numerical value of the frequency F to induce a peak value EMF in the loop, which is 2.369. So we need to find the frequency that will induce this EMF and which is a peak value of the EMF. So this is very similar to what you did it in your lab. In your lab, you are looking at the I think RMS value, if I'm not mistaken, but here we need to look at the peak value. So very straightforward. What you are going to do? You are going to first find psi. So psi is what? B bar dot ds bar. And here the figure is not given to us. So you have to formulate your figure. It is placed in the XY plane. So the square loop is placed in the XY plane. So therefore, to find the flux, and it is 0.5 meter side. So this is 0.5 and this is 0.5. And now you need to find ds. So it is dx dy. If you see here, dx dy az. So here, guys, if you see, there is no figure. So the EMF polarities are not given to you, right? The EMF polarities are not given to you. So that is not important to us in this problem, because in our problem, we need to find F. So we don't need to worry about this negative. So that's why I am not worried about whether it is minus AZ or plus AZ. So I'm just assuming it as plus AZ, and then I'm putting it as integral B bar dot ds. And this is equal to how much? This is 12 cos omega t. And if you see here, my magnetic field is not a function of space variables. Is it a function of x, y, or z? No. In that case, what will happen? B bar dot ds will simply become equal to B bar dot ds bar will simply become B multiplied by T. So B multiplied by ds. So where B is mu naught 12 cos omega t and ds is nothing but the area. B integral ds, which will be equal to B multiplied by S. And S is nothing but A square. So this is my psi, which is mu naught 12 multiplied by 0.5 square cosine omega t when I substitute A. And flux linkage, which is capital lambda, is 100 times psi because the number of turns is 100. So 100 times psi. And therefore my EMF is minus d uppercase lambda over dt, which is this. And now our question is, we need to find the frequency. That means we need to find this omega, which is 2 pi f, so that I can get a peak EMF value of 2.369. That is this 100 mu naught 12 times 0.5 omega naught square times sine omega t is equal to 2.369. Peak value. If it is peak value, then what will happen to the sine omega t? Sine omega t will reach the peak value, right? So it will be 1. And now from here, you can replace omega with 2 pi f and then find f, which is 1 megahertz. Okay, so remember in our experiment, you replaced it because we were working with RMS. So therefore you replace this with the RMS value. 0.707, if I'm not mistaken, 0.707 times the peak value, something like this. But here, it's not the RMS. We directly know the peak value. That's why you are changing it to 1. Okay, so this was the problem of our Faraday's law. Now, again, you have an example on our electromagnetic waves. So this one I will go a little bit faster, guys, because this is very similar to what we already did. It is saying that in free space, you have a sinusoidal time varying field and it has an angular frequency of omega, and the electric field is given to me. So the electric field is given to me, and look at it. This is which coordinate system? This is the spherical coordinate system. Spherical coordinate system. And then we need to find the corresponding instantaneous magnetic field intensity vector. So we need to find the corresponding magnetic field intensity vector. So since it is in the spherical coordinate system, so here I would suggest you that you directly go and use the Maxwell's equation. Don't use the idea which I showed you in the previous example, where you can directly find the electric field component using E cross H as the direction of propagation. That is okay for the Cartesian coordinates, but here it's spherical coordinates, so therefore it's better if you use the Maxwell's equation, which is del cross E bar is j omega mu naught H. So here you substitute your E, okay, so the left hand side, so you get the left hand side and then equate to the right hand side. This is your answer. And then you need to find the instantaneous form. So because this is in phasor form. So to find it in the instantaneous form, you know it. You have to multiply this by e power j omega t and take the real. And this is R. See, R. That means the direction of propagation is plus R direction. Direction of propagation. So that's why you have cosine omega t minus beta times a theta. And here you have sine. And the sine is coming because of this G. Okay, so you can go and you can check this one. Now, I want to take a couple of questions on the, yes, on the incidence. So we have taken the normal incidence, we have taken the oblique incidence. So the next two problems are on the normal incidence and the oblique incidence. So this is the normal incidence. So what is the question? The question is saying that you have a TEM, plane wave, which is incident from air onto a dielectric medium. That is y is less than 0 is air and y is greater than 0 is the dielectric medium. So this is my y. So this is my y is equal to 0. This is my y is less than 0. Y is greater than 0. So here is my air and here is my dielectric. And my boundary is this one. And your electric field is incident normally. So you have the normal incidence, then you will have the reflection, and you will have the transmission. Now, what is the question? The question is saying that the transmission dielectric medium is known to be non-magnetic and lossless. So this is my transmission medium. So it is non-magnetic. That means mu r your mu r2 is nothing but 1, non-magnetic. And this is mu r1 is already 1. The electric field of the incident wave is given. So this EI is given to us and ET is given to us. And we need to find the permittivity. That means we need to find epsilon R2 here. What is this? Epsilon R1 is air. We know it is 1. And what we need to find this. So how are we going to find epsilon R? Think from where you can get the epsilon R. So epsilon R's are usually under the umbrella of eta, because eta 1 is root of mu R1 mu naught over epsilon R1 epsilon naught, which for the air, it is 377 ohms. For dielectric, this is eta 1. So eta 2 is root of mu R2 mu naught over epsilon R2 epsilon naught, which is nothing but 377. This is 1. This is unknown. This is your eta. So your permittivity is under eta. And eta 1 and eta 2, how they are related? Incident field is given to you, transmitted field is given to you. So you can use the transmission coefficient, which is 2 eta 2 over eta 2 plus eta 1, if I'm not mistaken. And then if you substitute here, you will get. How can you get tau? Which is nothing but the transmitted electric field amplitude over the incident electric field amplitude. Now, if I compare this, my incident electric field amplitude is, and my transmitted electric field amplitude is, so this is 35 over 70, which is equal to 0.5. That's it. You got the answer. So you just go and substitute in your tau expression. See, tau 0.5 is 2 eta 2 over eta 2 plus eta 1, which is going here, and then solve it, simplify it. Put eta 1 value, eta 1 is 377 ohms. Put eta 2 value, eta 2 is 377 over root of epsilon R2. solve it, you will get epsilon R2 as 9. So this is an example of the normal incidence. So let us take one more example on the oblique incidence. So this is an example of the oblique incidence. So where my electric field is hitting the boundary of the two mediums at an angle. Now, what is the problem? The problem is saying that you have again a TEM wave, and it is incident from air onto glass. So this medium is air and this medium is glass. And the incident angle is 35 degrees. So this is my electric TEM wave, which is incidenting. And my angles are always measured with respect to the normal to the interface, because this is my boundary. And this is my air. And this is my glass. So this is 35 degrees. Glass is known to be non-magnetic. So this is the glass. So therefore, your mu R2 is 1. Epsilon R2, relative permittivity is given 2.25. This is air. So mu R1 is 1. Epsilon R1 is 1. And then you need to find the reflection coefficient. So the reflection coefficient is 1. But first, guys, please, you need to first identify, because we know that in oblique incidence, we have two types, right? Perpendicular and parallel. So which one is this? Parallel incidence or perpendicular incidence? Yes. Can anybody tell me, is it perpendicular or parallel? This is the first thing that you need to identify. And to find whether it is perpendicular or parallel, what you should do? You should look at the electric field vector. So if electric field vector is perpendicular to the plane of incidence, what is the plane of incidence? A plane of incidence is the plane where your incident, reflected, and transmitted field, all of them stays. So my plane of incidence is nothing but my screen, where all my incident, reflected, and transmitted, all of them are there. So if my electric field is perpendicular to the plane, that means if my electric field is perpendicular to the screen, then it is perpendicular incidence. If my electric field is tangential to the plane, tangential to this plane, then it is parallel incidence. Now, can you tell me what kind of incidence is this one? Is my electric field tangential to this screen, my laptop screen, or is it perpendicular?
Tangential?
It's tangential. See, this is the one. So it is staying in the plane. This is also, it is staying in the plane. Here also it's staying in the plane. It's not like this. It's not like this. This means it is coming out of the screen, or it is not like this, which is going inside the screen. That means this will be perpendicular. It's not the case. See here, it's like this. So it will have components. The electric field will have components in this direction and this direction, which is minus z and x. But minus z and x, they are in the plane of incidence, which is my xz plane. This is my plane of incidence. So therefore, I will conclude that it's a parallel incidence. So once I know that, then use that reflection coefficient. But remember, for the reflection coefficient, you first need also to know your transmitted angle, because your reflection coefficient is a function of incident angle, transmitted angle, eta 1 and eta 2. So eta 1 we can find out, see here. So eta 1 will be nothing but, it is 377 ohms. Eta 2 you can find out, which is root of 1 over 2.25 times 377, which is 377 over 1.5 ohms. Then theta I is given to us 335 degrees, and theta R we can find from the Snell's law. Theta R is nothing but theta I, which is 35 degrees. Now we want to find theta T. How can I find theta T? I can find theta T from Snell's law of refraction. Snell's law of refraction, which says that N1 sine theta I is equal to N2 sine theta T, or N1 is nothing but root of epsilon R1 sine theta I is equal to root of epsilon R2 sine theta T. So epsilon R1 is 1. So sine theta I, theta is what? 35. So sine 35 degrees is equal to root of epsilon R2 is root of 2.25 sine theta T. So from here, we can get theta T. So everything is known to us. Theta T is known to us. Theta R is known to us. Theta I is known to us. Eta 1 is known to us. Eta 2 is known to us. Then you can go and you can substitute in your expression, which is here. See? So you can go, this is my expression. This is for my parallel incidence. Eta 2 cos theta T minus eta 1 cos theta I over eta 2 cos theta T plus eta 1 cos theta. All of them, we have got it. See, this is the Snell's law. So from Snell's law, I got theta T as 22.48 degrees and theta I is 35 degrees. So eta 1 and eta 2, we have already got it. So eta 1 is 377 ohms. Eta 2 is 377 over 1.5, which is 251.3 ohms. Substitute in this expression, you will get my reflection coefficient as minus 0.141. And besides this, suppose if the expression is also given to you, then you can go and you can get the reflected field expression or the transmitted field expression, and the amplitudes of them, you will get it from the reflection coefficient. Reflection coefficient multiplied by the incident field. That will give me the reflected field. Okay, so this is the one. I think this is again very similar to what we have already done. I think, guys, it's time now. That's it. I think I have finished all of them. This is the last problem, if I'm not mistaken. So again, you need to find the magnetic field intensity vector here. So you can look at this. Oh, there is one more. Okay, this is another example of the EMF. So you can have a look at it. So this is my magnetic field and this is my loop. Okay, so you can, the idea is the same. So you have to first find psi, and then you have to find the EMF using psi. Okay, so
can you send the slides, Doctor?
Sorry?
Slides.
You can do the following, guys. So those who are not in my section, you just drop an email to me. This is my email address, which I'm sharing it with you in the chat window. Just drop an email to me for the